I want to welcome you to Advanced Strength of Materials, and today we'll be covering the relationship between stress and strain. So let's summarize what we've seen so far. So far we talked about the concept of stress, which is force per unit area, and we learned that there are 9 stress components that describe the stress at a particular point. But we also learned that the stress tensor is symmetric because of the conservation of angular momentum. And so really, in reality, out of 9 components of stress, only 6 of the stresses are independent of each other. For example, we talked about the diagonal terms of the stress tensor, and the stress tensor was given by this expression here, for example. And those diagonal components are the normal stresses, which cause the cube to either stretch or compress in each of the directions x, y, z. Then you have the shear stress components, which are the off-diagonal terms, as you can see here. And this stress tensor is symmetric. And so you have 3 more components, and those 3 components are the components that cause the cube to distort. Those are the off-diagonal terms. We then learned there's Cauchy's formula, which allows us to relate the tractions on the surface of the body, which could be oriented at an angle relative to the normal to the surface, to the stress just inside the cube, just inside the surface at that point. And we learned that that relationship is basically stress times the normal to the surface equals traction at that surface. There's 3 equilibrium equations that govern the stress state in the body of material. And there's also 6 strain deflection relationships. So this is what we've seen so far. And so if I were to show you the formulas so you can see them. So here are the 6 strain components. 3 of them are normal to the cube. And then you have 3 shear strains that really measure the angle change that you may experience in the body. And the stress tensor is symmetric, so this will be equal to that. And that can be verified fairly quickly by switching x and y. You'll see that you get the same answer if you did that. We also learned there's compatibility equations, and these compatibility equations ensure they have single valued solutions, and that and I also described that the derivations of these equations are expressed in my book. So we will not go over this in this particular lecture. But if interested, I can post those notes so you can see them. So there are 6 equations here. So these are your 6 equations that relate the strain to the displacement. And these are 6 equations. When I check, I have 3 unknowns, the deflections U, V, and W, which are the deflections in each of the directions, X, Y, Z. And so the deflection in the X direction, V is in the Y direction, W is in the Z direction. Those are the deflections of a point inside a body. And then I have 3 deflections, but then I have 6 strains. 1, 2, 3, 4, 5, and 6. So right there, you can see I have 9 unknowns. So I have 6 strains, 3 displacements, but 6 equations. So I have 9 variables total, but 6 equations. So something's missing here, as you can see. I need to have equal number of unknowns, but also equal number of equations. When I look at the stress states, the equilibrium states, I have 3 equations that describe the equilibrium of the body of material that I have. And we discussed that this can be derived using the force equilibrium. And we covered that in an earlier lecture. We used Newton's law, the integral form of Newton's law, to derive these equations. And as you can see here, I have 3 more equations. And I have 6 unknowns. Where are the unknowns? Well, I have equation 1, 2, and 3, but then I have 6 unknowns: 1, 2, 3, 4, 5, and 6. And remember that the stress tensor is symmetric, so this is equal to that. This of diagonal term is equal to that. This of diagonal terms is equal to that. So remember that. So on the surface of the material, we also have Cauchy's relationship. We covered that just a second ago. And the stress tensor is symmetric. So when I look at the totality of the situation, we can then count all the equations, right? So we have 6 stresses that are unknown. That's your 6 stresses. Then I have 6 strains that are unknown. And then I have 3 deflections. They're unknown. And there's U, V, and W. So I have a total of 15 unknowns. And yet, I only have 9 equations I've covered so far. 6 are the strain displacement relationships. And then 3 equilibrium equations. So I have 15 and 9. I'm missing 6 more. Let me show you the 6 strain displacements again. And let's clear all this so that it's not, you can clearly see what they are. These are your 6 equations. Let's clean this up. So you can see I have 6 equations there. 1, 2, 3, 4, 5, 6. And then I have the equilibrium equations. If I continue counting, 7, 8, 9. So you're kind of stuck now with 15 equations, 9 equations, but 15 unknowns. And where I get the rest of them, I'm going to use stress-strain relationships to get 6 more. And if I can get 6 here, then I have 15 unknowns and 15 equations. And then I can solve this, which sounds very daunting, to be honest. So where do you find the stress-strain relationship? How you find that relationship? You find that relationship during testing. That's how you find that relationship. Stress is related to strain. And if I can find that relationship, then I have gone really far now. So how do you do that? So how you conduct a test to determine the relationship between stress and strain? The first one of the tests that's done is called a unidirectional test or tensile test. What you see here is called a tensile test. And typically, you have regions that are thicker to ensure that the failure occurs in the center. That's how that test is done, okay? And that test will typically be done in an instrument machine like on the right, and it will be, you have deflectometers that measure the deflection, you know the initial length, and then you know how much this is moving, so they can calculate the strain as the axial strain, epsilon xx, if this was in the x direction. You apply a load P. And then you can calculate strain as the change in length divided by the original length. So that's what you will typically see. And the stress will be calculated as the load applied divided by the area, this cross-sectional area. And typically the samples tend to be round, so it will be P divided by pi radius squared. And so if you have this relationship and you have this relationship, I can plot this versus that to get a relationship between stress and strain. And now that's helping me now populate what these 6 equations are. We'll get there in a second. And so I have a picture here at the bottom, and that picture shows the gauge length. So we call that the gauge length, which is where we would like to see the failure occur. We call that the gauge section. That's where I would like to see the failure occur. You can see clearly that the sample has grown in size from here to here, and that length L is longer. So depending on the material being tested, you'll use an MTS machine, say. You can use the ASTM standard that provides the procedures on how the test is done. The gauge length might be taken as a distance between the grips from the machine. And that way you can then determine what the strain is. Another approach that's used more modernly is called digital image correlation, where you put a speckled pattern on the sample and then use cameras to measure the strains in that way. So let's look at the stress strain curve. When you do a test like this, and like I said, you'll take sigma xx, which I erased, but it's a load applied divided by the cross-sectional area, radius r. And then the strain is simply the change in length. So this length that occurred due to the load applied, length divided by initial length divided by initial length. So I'll plot this versus that. And for a lot of metals, you're going to see a behavior that looks like this. This is called the stress strain curve. And the stress strain curve provides the characterization of the material. You typically have a proportional limit, an elastic limit, the yield point, and then you have the ultimate strength, which is the highest strength you may see in the body, in that sample. And then you're going to have, as you apply the loading, displacement control, you have the rupture strength. So those are the 3 points. I'll cover the dashed line later. For now, I want you to see that as I load up the sample, I'm going along that curve. That's the curve I'm following as I load up the sample. On the right-hand side, what you see is the comparisons of what various stress strain curves look like for various materials. Obviously, this is a depiction. The point being is that the stress strain curve varies upon the material that you select for a particular application. So if I were to study this curve a little bit more, what you see in the left-hand side is structural steel as an example. And you can see that the units are load per unit area. And the strain is dimensionless with no units, or units of length per length. And so I'm just showing an example of structural steel on the left side. On the right side, what I'm showing is that this slope here, the initial slope, is the Young modulus. So in the linear elastic regime, sigma xx is equal to E times epsilon xx. And that makes sense because I plotted stress versus strain, and it goes through zero. So therefore, the slope E has to be that one. You typically, at least in aerospace designs, you want to try to design so you stay below the yield point. You want to stay in that zone linearly. You can't go above yield, but then you have to look at the potential effects of fatigue, form, fit of function could be affected. You want to make sure that there are no other potential failure scenarios of concern. So at least in aerospace design, we try to design so we're staying below yield. That's the idea there. The problem is it's hard to achieve for a lot of components because, for example, engine components get really hot, and so you get some amount of yielding. And the yielding is occurring in this zone, for example, the zone between B and C. And I'm blowing up B and C. So I'm blowing up this region here so you can better see what's going on the right-hand side. So I'm blowing up that curve. I'm zooming in between points B and C there. Further, as you load up the sample, you start to get some strain hardening. And that means that the stress is increasing with increasing strain. And then from this point downwards, you start to get necking, which is a cross-section that starts to reduce in cross-sectional area. I'll cover the true stress strain curve later, but I wanted to focus on that. So the second thing you see in this image is some labels at the bottom that say elastic range and plastic range. What that means is if I am here along this and I unloaded, I'll come back to zero. So there's no additional loss of energy. Like a rubber band, if you apply a small amount of load and you let it go, it returns back to the original state. And so, as you can see here, if you stay in the elastic regime, it goes back to zero. But the minute you start yielding the material, then you're going to start getting some plastic deformation. And typically, when you unload, you're going to unload in this way. Not always, but in many cases, you unload parallel to this curve, to the initial slope. And the same could be here. And the reason is because you're recovering part of the elastic strain that you had encountered. So typically, strain total is strain from elastic plus strain plastic. This strain can be recovered, and that's why this curve, a lot of times, it returns parallel to the initial slope because of that. And there's two different materials that can be talked about. two materials that can be classified as ductile materials or brittle materials. Ductile materials are those that the percentage elongation to failure is 5% or more, while brittle materials fail at less than 5%. Ductile materials go under a lot of inelastic strains prior to failure, and so you start seeing that there's so much deformation that necking starts occurring, as you can see there. The cross-section reduces quite a bit, and there's a lot of examples of materials that do that. Brittle materials, on the other hand, have barely any necking, and the failure usually occurs at a 45 degree. Doesn't have to be 45, but most of the time it does, and exhibits very little deformation before rupture. And as a result, failure occurs suddenly without any warning. It just happens without any warning. So again, brittle materials could be like glass or concrete, cast iron, titanium. Certain titaniums can behave that way. Another thing I want to point out is the stress strain curve can be looked at. If I magnify in here in the stress strain curve here, I'm magnifying here. You can see that when I go up to a particular load, I would like to define yield in a smart way so I can use it for design. And so why is that important? So if I choose yield here or yield here or yield here, it's unclear where the nonlinearity starts. And so rather than being kind of arbitrary about that, what people have thought about doing that works very well is to take a 0.2% offset. So you take this line here, and you move it 0.2%, and you draw a line until it hits this curve, and then we call that the yield strength of the material. And that way it's not arbitrary. Because person A could say, well, I think it starts to curve around here. Somebody else could say it's here. So you can define it more consistently by using that parameter, that 0.2%. So that's industry practice, okay? If you want to be conservative, you could draw a line, and then it becomes, it goes away, then you can call that's too conservative. But I've seen people do that in design, in industry. And finally, I covered this already, but a lot of materials go over here, and then they come back. They can come back to zero in this zone. But past the yield strength, you typically have this permanent deformation that occurs, as you can see here. But when you reload it back, it goes back through here, as you can see in the image on the right here, that image here. It loaded, and then at point A, unloaded over here, and then that's the amount that recovered elastically, and that amount is elastic recovery, while this is a permanent strain. So what I've shown so far is how you'll deal with taking the stress state and dividing it by the original cross-sectional area, and the strain is also divided by the initial length. So when you construct a curve like that, we call that engineering stress strain curve. Engineering stress strain curve. If you use a finite element software or some software, they may require you to provide a true stress strain curve, which means that the stress, as you apply the load, the cross-sectional area is changing. And so some codes ask you for the true stress strain curve. In that case, sigma xx is going to be measured against the current area. And the strain will also be measured against some sort of length that's changing. So as a consequence, you can determine what the true stress strain curve looks like by taking this integral of dl divided by L. And when you do that, you get a log of L divided by L naught, which is really 1 plus epsilon. So if I know epsilon, which is the engineering stress, engineering strain, which is equal to L final minus L or L current divided by, let me write this again, L, the current length minus initial length divided by initial length. That's what this is. So if I know that strain, the engineering strain, I can take that strain and calculate the true strain, the strain referring to the current length. And the true stress can be calculated as the engineering stress using the original area from the cross-section I started with, and then I can multiply by 1 plus epsilon, where epsilon is the original, is the engineering strain. So you can very quickly take an engineering diagram, this diagram here, you can take that, and easily convert it to the one at the top. So yeah, so that's the process there. And I will give you extra credit if you're able to show me that this curve engineering diagram at the bottom, that solid line, using the formulas on the left, convert quickly to a dashed line. So you will get extra if you can submit that work. So the engineering strain is strain, and I covered that, but I'll repeat it again. Final length or current length divided by initial length divided by initial length. It's what we call it all the time, strain. I'm trying to explain to you that's the engineering strain. That's the nomenclature that is used in this area of expertise. Okay, so all I did here was one-dimensional. But the problem is I have 6 components of stress and 6 components of strain. So I have sigma xx, I have sigma yy, I have sigma zz, etc. But I have epsilon xx, epsilon yy, epsilon zz, and so forth. What do I do? Because I have 6 components here and 6 components here. And these 6 components of stress should be related to 6 components of strain. So yes, here I showed you 1D, like what happens when I apply a load in one direction. In one direction, I apply a load P, which produces a sigma xx, and it obviously produces epsilon xx. But what I do when I have 6 components of stress and 6 components of strain, that tells me that there must be a matrix that relates the stress to the strain. There must be something there. And I can write it for you. It looks a little bit scary, but it's not. All I did here, and I switched to numbers, and I apologize for that. In a lot of books, they use different conventions, and I don't want you to be worried about that. Here at the bottom, I show you. So sigma 1 is sigma xx, sigma 2 is sigma yy, sigma 3 is sigma zz. These are the normal components. Sigma 4 is YZ, the shear stress. 5 is XZ, and 6 is XY. And that's a convention that you'll see books use. The convention I'm showing you here with numbers like that is called contracted notation. So that's what it's called, contracted notation. But at the end of the day, it's the same stuff. These are the normal stresses, and these are the shear stresses. But it needs to be in that order as I show you here. That's a convention that industry uses, and I think you want to learn it. Okay, so this looks scary. Maybe it looks scary, but I don't want you to be worried about that. So just to make sure it's clear, I'm using contracted notation, which is pretty much simplifying the write-up so you don't have to write a lot of variables. But sigma 1 here is sigma xx. Sigma 2 is sigma yy. Sigma 3 is sigma zz. So it's the same stuff we discussed so far, and that is what's used in industry. Now, this may look scary, right? But it is not scary because you have 6 stress components and 6 strain components, which also use contracted notation, as you can see here on the right-hand side. At the end of the day, if you have 6 stresses and 6 strains, there must be something here that relates the left-hand side with the right-hand side. So if I have a vector of 6 components here and 6 components here, then I have to have a 6x6 here of some kind. So I do have 36 components that are here. It turns out there's symmetry. So in reality, I have only 21 independent constants that need to be measured. And the question becomes, how do I measure those components? And the answer is simple. I go to the test labs and I test it and I find out what each of these constants are. That's how I measure that. That's how I find this relationship between stress and strain. As you saw earlier, much earlier, these equations came from straight mechanics, okay? Using geometry, mechanics. This came from Newton's law. But this one here, this relationship here is empirical. It comes from testing. And these are all numbers that you measure. These are all things you measure. We already talked about one of the numbers that we measure, which is modulus, right? So, okay. I could invert this relationship also. I could invert this relationship and say, okay, I can relate strains to stresses. And instead, now I have the inverse of this matrix here. So if this is C, well, then this is C inverse. Here is called compliance matrix, while here is called stiffness matrix. But at the end of the day, I don't care, because all I'm trying to point out to you is that you have 6 components of strains that are related to 6 components of stress. And there must be something here that connect the two. And how I measure that, how I figure out these numbers, I do testing. That's what I do, okay? So let's start with a very simple test. But I'm going to cover pure shear first, okay? If I apply torsion only, just torsion here, what people have found is that you actually, by doing that, and if I take a little square, what you find is that you get only pure shear. You get nothing more than just shear. So there's normal stresses, nothing. This causes this square here, and that makes sense, you can imagine. It's going to make that square distort and shear. If I apply a shear like that, you expect it to distort like that. It makes sense that you should do that. I invite you to check it out at home. Maybe take a cylinder of some kind and rubber and then draw lines. You know, I guarantee you that if you drew lines on a rubber and you rotated that cylinder made of rubber, it's going to start rotating like that, and the angles are changing. right? I'm exaggerating, obviously, but that's what shear does. Shear distorts the material. And so if I look at the stress tensor, there's no normal stresses, right? And I'm looking at only shear stresses in the XY plane. So if this is X and that's Y, they're only happening in the XY plane. But it turns out that if actually measured the angle, so if I apply a load here, T, torsion, and I calculated the stress due to that torsion, I can do that calculation. I can actually then also look at how much the angle of a square is changing, right? The angle change. And that angle change is gamma xy. And this is sigma xy. It turns out I can measure this, so I can tell exactly how these two relate. And that turns out to be the shear modulus times gamma xy. And this can be measured through a torsional test. And there are standards that can be followed to measure that. Okay. So that's how you deal with that. Okay, so I apply a torsion load. I know how much these points are getting rotated by. So I can calculate the angle change from this test. I can calculate the shear stress. I can then plot this versus that. When you plot it, you can get this. You can get that slope. And that slope is G, or the shear modulus. And that means that sigma xy equals G times gamma xy. But I can repeat that test to all the other different angles. And if I do, then I get this expression. I switched to them purpose so you can see. Then literature, you can see different variables used, but X is, in this case, is 1, Y is 2, Z is 3. If I repeat the torsion test in other directions, then I get the same equations. And what I did, I kept this here on purpose. Because in composite materials, you could have different shear modulus depending upon how you test the material, what direction you're testing it. Composite materials are those that have fibers going up, say, for example, isotropic materials. If I cut the sample here and I test the sample, it will give me the same modulus as if I cut the sample this way, or I cut the sample this way. That's called an isotropic material, where properties do not depend on direction. So if I blindfolded you and ask, okay, cut a sample out of this metal piece, like this one, and I say cut it again at some random angle, and I say, okay, now do a test, theoretically, the modulus should be the same if it's isotropic. And what I did, just explain it better, I'm making it more general. Okay. And what I mean with that, and I think it's worth doing it in this class, since it's an advanced course, why not? Is that composite materials will have fibers going in one direction, maybe. You can have also woven composite, these unidirectionals. But you also have woven composites where you may have fibers going this way, but also going this way. Now, this is not a composite class, so I don't want to spend too much time. But my point being is, if this is a one direction, and that's a two direction, and that's a third direction, then it is possible that instead of having a single shear modulus where you, if it's isotropic, then G12 will be equal to G13 equal to G23. That shear modulus will be equal, but to keep it general, they could be different. That's the point I'm trying to make. So the shear modulus in this plane, G12, could be different from the one in the plane of G13 and different from the plane in G23. But if it's isotropic like aluminum or steel, then G12, G13, and G23 will be approximately equal to each other, and you're done. So one of the things you notice here is, if I have a shear stress applied, the only shear that's involved is that angle change. But you don't see that square growing in size, because epsilon 1, epsilon 2, epsilon 3, what they do, they measure the amount of stretching and compression. And this one measure the angle change in the other two planes. So if, and to explain it better, if I'm applying a torsional load or some kind, maybe this square is getting angled like that. So it's distorted. But what we're saying by saying that this is zero is we're saying that the angle change in this plane is not getting affected. The angle change in this plane is not getting affected. So that's what I'm getting you know, that's what I'm really describing. So therefore, we can state with some certainty that these are zero if I apply a torsion load like I did here. If I apply a torsion load like I applied here, I don't expect an angle change in these other two planes, and I don't expect this square here to expand in other two directions, as you can see here. I don't expect those to show up. Those other strings shouldn't show up because I'm applying torsional load. There should be only angle change. So the same thing goes with the other items here. I can apply a torsional load in other planes, and I get the same conclusion. So because of that, what ends up happening then is that you get a situation where all the shaded terms must be zero. And they have to be zero because of this reason that we just discussed. And you can check it at home that is true. Like if this is true, you can check that the shaded terms have to be zero. There's just no other choice. The other thing we say that's helpful here in this whole derivation, that I think will make a lot of sense to you, is that if I took a square rectangle and I apply a load P axially, and that corresponds to a strain epsilon 1, say, in the one direction, I don't expect the square to change angles like this. It doesn't make sense. I expect the square to kind of stretch if I apply a load the way I'm applying it right now, okay? For that reason, if I apply just these stresses, then the shear strains all should be zero. And that's why you can see that if I'm applying just normal stresses, then there should be this all should be zero. Like it doesn't make sense that this will show up. Because these three are connected to these three, which are the shear stresses. And these are the normal stresses. So it makes sense. It makes total sense that those should be zero. So I invite you at home to check it out and maybe try some calculations, and I think you will see that that must be the case. Okay. Okay, so we're gonna now step into something more. So continuing on here, we'll continue on here. I want to cover something more that's quite interesting that's going to come up later as I go through this. is that if I were to apply a load P like that, what it turns out that people have observed this, is that the cross-sectional area that you see there reduces in size if I apply a tension load. And if I apply a compression load, like the opposite direction, then the cross-sectional area grows. That's what people have observed. We call that the Poisson effect. Poisson. Let me write it for you so you know what I'm talking about. Poisson effect. When I apply tension, the cross-section has been shown to contract. Part of that has to do with volume, right? The volume has to be preserved to some level. And for that reason, then the body of material has to contract. And there's a limit of how much you can contract. So the Poisson ratio is really, if I apply a load in the epsilon XX direction, then the Poisson ratio is measuring basically how much is contracting the other direction, what fraction of that is. So this is kind of like the fraction of how much that is. So if this moved an amount or the strain in that direction is epsilon XX, and I put a strain gauge going that way that measure that strain, the ratio of these two numbers gives me the Poisson ratio. Most materials have a Poisson ratio that's closer to 0.3. But if you have a rubber material is going to have a Poisson ratio of 0.5. And you see that a lot. If you take a piece of rubber and you pull it, you're going to see the cross-section quickly decreases in size compared to if it was aluminum. So clearly, when you stretch in one direction, it contracts in the other. And there's a negative sign because it makes sense. If I apply a positive load in one direction, so it stretches, it contracts. So these negatives, so say epsilon XX is 0.01, epsilon YY in a test, say, could come out to be negative 0.003, say. I'm making it up. Because it contracts, the square that was here became smaller in this direction. Okay. In fact, let me draw it better here. So a square that's like that initially is going to turn out to be, if I apply a load in that direction, is going to become smaller in that direction, but longer in this direction. Right? And so the Poisson ratio will be positive based on that calculation. It turns out that the shear modulus, incredibly, is related to the Young modulus through the Poisson ratio. So I can do a test. Let me show you this. It's incredible. I can do the very test you see in the top left, okay? That top left test, if I apply load P, I can calculate sigma XX. That's P divided by area, initial area. We also learned that I can calculate the strain from the final length or current length divided by initial length divided by the initial length. So I can plot this against that. I can plot that. So let me do it here. And that gives me a slope. That's your modulus, right? But the coolest thing is I can also put a strain gauge here going in the y direction, in that direction. And I can plot it too. Okay. And I can then take the ratio of epsilon YY to epsilon XX to get the Poisson ratio. Okay, great. Then I can do another test. And that test, I'll apply a torsional load. And that test will give me sigma xy equals G times gamma xy. What is incredible is that this E, this Poisson ratio, and the shear modulus, they're all related through this expression. That is what's incredible about it. In that very simple way. I already covered what isotropic materials are, so we'll just keep moving. And isotropic is the opposite, where the properties vary dramatically from one direction to another. So Poisson ratio is not a failure quantity. Poisson ratio is a measurement of how much, when you stretch the material in one direction, how much it contracts in the other directions. That's all it does. And for rubber materials, close to 0.5, and for other materials, tends to be closer to 0.4 to 0.3 and so forth. Okay, so continuing on then, I can do an axial test then in that case. So let's just do an axial test in this direction. Okay. Well, that stress is this one, because that's what I applied. But everything else is zero. I don't generate the shear stress because I applied this axial load. Obviously, everything else is zero because that's what I applied. It turns out that we can figure out what is going on here very quickly. And I think we can do it together and figure it out, because it's going to make a lot of sense in a second. Let's look at this carefully now. So let's do it together. So if I apply this load sigma, which is what you apply in the test, I know that the strain, I already told you that the stress equals E times epsilon, which is this one right here. And so I can solve for epsilon. That gives me sigma xx divided by E. But I also know from the same test, I can tell you what the Poisson ratio is. I can tell you what epsilon yy is, because I can measure it in the test. And we know that because I will measure it by putting a strain gauge here. Epsilon yy is going to be, by definition, this, a percentage of that strain that was measured, but this way. We already talked about it. But hey, wait a second. Isn't this also equal to minus nu times sigma xx divided by E? And so that's exactly what you see here. We know epsilon xx is this one here. And in the other direction, which is out of the plane of this sample, you get this one here. So you quickly see that the strain epsilon xx is that one, epsilon yy is that one, and epsilon zz, I don't want to repeat it, but it's going to give you this one too. It's going to look like that. But just like it contracted in that direction that you see here, out of the page, it's going to also do the same thing. What I can do, I can repeat this experiment in the other directions. Okay, you can repeat that experiment. So here I did it in the X direction, but I can then do it in the Y direction, then the Z direction, and so forth. So let's do an example with composite materials, just because that's what is, composites are used quite a bit, so you can learn how this is done. So I apply a load sigma 1 in the test, and I get this modulus. I can measure that using a test just like this, okay? And then I can measure the Poisson ratio. And the Poisson ratio is going to be load applied in the one direction, measuring the contraction in the second direction. That's what the two indices mean. Now, earlier, I didn't use indices because these for isotropic materials, but for composites, the Poisson ratio can change depending upon how you test. And so I'm going to track that now. So again, the first number represents the load direction that's applied, and the second number represents the direction where the contraction is occurring. Obviously, if I apply a load in the one direction, like here, this is the one direction, then I expect it to contract in the second direction. And so, but from this equation, I know that epsilon 1,1 is sigma 1,1 divided by E11. And then for epsilon 3,3, I can then calculate that. So the stress in the one direction produced all these strains. I can repeat the testing that I just did in the two direction. So if I apply a load in the two direction, I will get this, and it will contract in the other two directions. I can repeat the test in the third direction, where I apply the load in the third direction, but it contracts in the other two directions. And then I can use superposition. I can then add up all three stress directions to create this matrix that you see here. As you can see, this 6x6. It connects the stresses, the strains, to the stresses. By symmetry, this has to be equal to this. And what you see here is that if it's isotropic, then E1 equals E2 equals E3 equals the Young modulus. And the Poisson ratios, all the Poisson ratios become nu, and all the shear modulus become just this one. And in this case, for isotropics, you also have this relationship that relates everything else together. So that's how you calculate the strain-stress relationship. So, all right, so we'll continue here. I'll write it in equation format. So matrices can be scary to look at, but if I look at isotropic materials, then it looks as simple as that. And you can see that here, that if I apply a load X only, so then I have sigma XX, then these are 0, and then you get exactly what I discussed earlier. So you can see that works out. You can see these ones work out. We discussed that, the torsional tests. So this looks very familiar, and you can see it works out very nicely. So you can see that everything we discussed is pretty much what you see here. Like, it's all working out. For example, let's say I have a tension test. Sigma XX, sigma XX. Well, nothing else. No, there's no other stress. So that's 0, that's 0, that's 0, that's 0, that's 0, and that's 0. Okay, let's look at the strains to see if these equations work. You can see that the strain in this direction, epsilon XX, should be sigma XX divided by E. We talked about that the slope was modulus. Okay, that looks good. What about this way, the y direction? Epsilon YY is supposed to be, according to what we discussed, the negative nu epsilon XX, and that nu does not look like nu, so we'll fix that. And that's negative nu times sigma XX divided by E. You can see that that's exactly what we're getting. That's exactly what we're getting. In the Z direction, the same thing. So I'm not going to repeat it. So I will invite you to do, I call this virtual test. Do a virtual test in your head so you can see that these equations do hold water, and you don't have to even memorize, because that's exactly what happens physically. You can invert the relationships on the top left to write in terms of stress. So if you write it so that the stress is in the left-hand side, then you get these relationships that you see here, 6 equations that was missing. If you remember, there's 6 equations that were missing. I found them finally. Here are the 6 stresses that we've been looking for. One thing to mention is that the way I wrote it here is different. So here, E needs to be defined, and this is the summation of the diagonal terms of the strain tensor, which represents the volume change. We discussed that. And lambda here has this expression that looks a little more complicated. So this one is the easiest to remember. You can try to memorize this on the bottom right. I haven't never memorized it, but the top left is physical, so you don't have to memorize that. That one you can derive yourself with no book. Bottom right is a little bit harder to do. So, but again, you can find this bottom right expression by simply inverting this stiffness matrix, this compliance matrix. If you invert that, then you can get these equations here fairly simply. This equation that I showed you earlier, this equation is exactly what I showed you a minute ago. Instead of having the 1 over E here, I had it here pretty much. But these for isotropic materials. That's how I had it in the previous page. And if D is divided by E, because I'm removing it from here, then you see this G now. And what I did, I added another term here so you can see how to treat thermal effects. And the alpha here is called the coefficient of thermal expansion. While delta T is a change in temperature. So I can calculate the strain due to changes in temperature and coefficient of thermal expansion is known. So what you see here is a constitutive law for materials that also have thermal effects. You can invert this relationship, the very one that you see on the screen, by using MATLAB. And when you do, the equations look more complicated. But these equations, this one and this one, are the same ones as you see here. The ones here is this one, but with no thermal effects. And the one here is the same as this one, but with no thermal effects. But they're basically the same thing. Okay. You can check it at home that it's the same expressions, but written in matrix format. Okay, so what happens when you apply hydrostatic compression? So I apply compression in all 3 directions. And you can examine that. You can look at what's going on when you do that. If I apply a load P in all 3 directions, so basically put a cube underwater, it gets pressure in all 3 directions. We call that hydrostatic compression. So the stresses in all 3 diagonal terms become P, for example, in this case. That makes total sense. So then what is the strain? So let's look at that. And how do I do that? So what I can do, I can substitute P minus P here, minus P here, and minus P here. And when I do that, epsilon xx becomes 1 over E times minus P minus 2P nu. And then minus P can extract out like this. And that's a strain in that x direction. But it turns out that epsilon yy will give you the same answer, and epsilon zz will give you the same answer. I'll invite you to do it at home. And so therefore, I do think there's a sign problem in what I did, because this is negative P and that's negative, so that gives me positive. I apologize. So this will be negative. And so now you can see that expression matches what I have here. So the diagonal terms have those strains. And it turns out that if I add these terms, that gives me the volume change as we discussed before. And it turns out if the Poisson ratio is close to 0.5, like rubber, say, then you're going to get almost no volume change, right? Because nu is 0.5 and 1 minus 2 times 0.5 is close to 0. So if you have rubber and you apply compression in all directions, it's going to be very hard for you to compress it, okay? It's going to be very hard for you to make it compressed. But if it was metal, it's a little bit easier. And you can see that's the truth, because nu will be like 0.3, not 0.5. And if it is 0.3, then it can have volume change. And the ability of having volume change can be measured by adding these terms here, right? If I add all those terms here, you get 3 times 1 minus 2 nu E times P. If I invert this relationship, I get K. And what K gives me is the ability of the material to compress. So if nu, in this case, for rubber material is close to 0.5, K is going to give me close to infinity, which means is K tells me is the bulk modulus, and it tells me how difficult it is to compress something. So if K is infinity, it will be very, very hard to compress it. Yes, it's very interesting. It's very interesting to realize that I'm talking about rubber, applying compression all 3 directions, it will be almost impossible to reduce its volume. And then the other points I want to make is that based upon everything else I discussed with this K, this bulk modulus formula, and this lambda expression here, and the shear modulus one, there's this table here that's very helpful in showing how everything relates with each other. I'm not going to ask you to memorize this. For example, you can see here the shear modulus here. They call it mu, but I use G. So you can see that E and nu are related to G based on the same formula we talked about earlier. See, it's all right there. The bulk modulus, which measures how much the volume changes, right there. Is this one here. You can see that that's there. And the bulk modulus can be measured. You can actually do that testing to measure it. A lambda, I already showed you that earlier. So all the expressions we discussed are here. They're just showing you how to relate one versus another. You're not going to use this, but it's a handy table to have. If you have my slides and you go to industry, you can probably use this. Okay. This is just to show you the relative comparison of different materials. And as you can see here, I'm showing you modulus, I'm showing you Poisson ratio, and I'm showing you the shear modulus, so G. Don't worry about lambda for now. But the coefficient of thermal expansion is very useful for design. You can use that. And K here is the bulk modulus, right? So you can see here that some materials have the ability of, you know, it's easier for some materials to compress than others. So, but anyway, so this covers the materials on stress strain law. And so the point I have to make here then, just going to summarize here, is that we have 6 stresses, 6 strains, 3 displacements, 6 strain deflection relationships, 3 equilibrium equations, but I found 6 more that relate stress to strain. And now the story is more complete. Now I have 15 equations and 15 unknowns. The story is a lot more complete, and that covers the lecture on constitutive law.